I must apologise now to our next speaker as we've run a little bit over time. I'm very sorry. But it gives me now great pleasure to introduce to you the first speaker of the evening, Professor Tim Horbury, who is going to deliver the Christmas lecture on the Parker Solar Probe and Solar Orbiter spacecraft. Professor Horbury is a professor of physics at Imperial College London. Shall I let you set up while I'm...
Sure, yeah, that's good.
Yeah. I just thought of that. I should have done that before. His scientific interests lie in the study of the sun and its effects on interplanetary space and the Earth. He has formal roles on a wide range of European and American missions, including Bepi Colombo and Parker Solar Probe. He leads the team that built magnetic field instruments for ESA's Solar Orbiter and NASA's IMAP missions, which launched in February 2020 and September 25, respectively. And he is developing instruments for NASA's upcoming multi-spacecraft Helioswarm mission. Over to you, sir.
Thank you. Thank you. Okay, well, good afternoon, everybody. Thanks very much for the invitation to be here. It's great to see so many people out this afternoon. What I'm going to talk about today really is stars. So, throughout human history, people have looked up at the night sky, seen these thousands of stars and wondered what they were and whether they affected our lives. And it's only in the last few hundred years that we do know exactly what stars are. They're hot balls of gas undergoing fusion. And no, actually, they don't affect our lives. Excuse me, sorry, thank you. Apart from one of them. Because most of these stars, countless billions in our galaxy, are unimaginably far away, apart from one, which is far closer than any of the others. More than 200,000 times closer than the next nearest star. And it's close enough that its light turns night into day. So that's the sun. So the sun is a star, we now know, like many others. And it's extraordinarily close compared to all of the others. And that means that we can study it in ways that simply aren't possible for any other star. So by studying the sun, and as I'll show you, we can fly through the atmosphere of the sun now, we can understand stars in general. But it is the only star that also affects our life. So the sun's heat stops the Earth from freezing. The energy from the sun in the sunlight powers almost all life on Earth. And so obviously it's a very positive object for us, and it's something that we want to understand in terms of how it affects our lives in positive ways. And but it also can affect our lives in negative ways as well. And that's something that I'll talk about during this. So what do we know about the sun? Well, if you look up at the sun, you shouldn't look at the sun, whatever. If you do look at the sun, it's a kind of fairly featureless ball. Since Galileo started looking at with telescopes, we know now that there are sunspots on the sun. This is the sun yesterday in white light. And we now know from those sunspots that you can see that the sun rotates. You can see it going around roughly once a month, every 27 days or so. And we've known for hundreds of years that the number of sunspots on the sun actually varies over time. So it varies with an approximately 11-year cycle that we call the solar cycle. We've actually just gone through the maximum of that cycle when there were the most sunspots. And as I'll show you, that's related to actually magnetic activity on the sun. So we now know that the sun has a very strong magnetic field, much stronger than the Earth's. In some ways similar to the Earth, it's generated in a similar way, but it's much more active, as I'll show you. And in particular, we know that although the Earth's magnetic field actually reverses every few 100,000 years, the sun's magnetic field actually reverses every 11 years. It actually tips over every 11 years, and that's what causes this cycle in the sunspot, as we'll see. So, although one of the themes of this talk is the sun, another theme is actually going to be magnetic fields. So the activity on the sun is driven by magnetic fields, and the effects that it has on our Earth in terms of what we call space weather, those negative effects, is also driven by magnetic fields. So as I'll show you, measuring magnetic fields is enormously important, and that's why it's one of the things that we do at Imperial College. So in terms of those effects, this is a movie of the aurora. This is taken from the International Space Station. This is a very positive effect of the sun. I don't know how many of you have ever seen an aurora. It's a pretty spectacular thing if you do. What I would say these days, so there were quite strong auroras in May last year. They reached down to London as well, so I saw it in South London on the way home from the station back to my house. They're a lot better in the photos than they are in real life. So the photos I've got of it are a lot better than it actually looks like. So if you haven't seen an aurora, don't worry, they're not quite as good as they look in the photos. So the aurora is a really lovely thing, but that's actually a manifestation of the way that the sun is interacting with space near us, and in particular, interacting with the Earth's magnetic field. What you're actually looking at when you look at an aurora like this is charged particles racing down magnetic field lines and hitting the top of the Earth's atmosphere. And those particles have ultimately come from the sun. They hit the top of the Earth's atmosphere, and they make the atoms glow, and that's why you see the colors that you do. So when you see this, it's a very nice thing, but as we'll see, some of the effects of that are actually very negative ones. And as we develop more technology, and we become a much more technological civilization, as a result, we become actually much more dependent on those effects, and they can have surprising impacts in places that you wouldn't necessarily expect. So we now know that the sun is a... excuse me. Okay, it's jumped on a couple of slides. Sorry. Let me move on to that. So, I apologize. I don't want that to work. Oh, no. It'll be fine. Nobody panic. Okay. So, we now know that the way the sun affects and interacts with us is because its hot atmosphere, which is up towards 1 million degrees, actually expands off into interplanetary space and blows a bubble in interstellar space. And that bubble is called the heliosphere. It carries with it the sun's magnetic field. So this is a little bubble of particles and magnetic field that goes out beyond Pluto, so it's more than 100 times further away than we are from the sun. And that little bubble we call the heliosphere. We all live inside that bubble. And that bubble actually protects us from a lot of negative effects in the galaxy as well. It shields us from most of the galactic cosmic rays that come and arrive near the Earth. I don't know if you heard the story from a couple of weeks ago about lots of aircraft were grounded, lots of Airbus aircraft were grounded over a weekend. That was precisely because of the effects of galactic cosmic rays on the electrons inside the aircraft. So the sun helps us, not completely, but it shields us from a lot of those effects as well. So as a result, therefore, the sun is the only star that affects our lives, and it's therefore something that it's worth measuring because we can understand how stars work. It also is important because actually the processes that we measure in interplanetary space, things like shock waves, turbulence, the way particles are accelerated, are the same processes that happen throughout the universe. So if you want to understand, for example, the acceleration of the fastest particles in the universe, supernova shock waves, it's really hard to do from here. You can't measure it directly. We can fly a spacecraft through a shock wave in interplanetary space and directly measure the particles and what's happening. So it lets us study the same processes. But also, as I said, the sun affects our lives, and so it's something that's important to study because we want to understand how those processes happen. And this picture here is a total solar eclipse. This is actually from the, when it was April 24 total solar eclipse. I don't know if anyone has seen a total eclipse. I imagine quite a few people here have seen total solar eclipse. Most of the audiences I speak to kind of haven't, but I think many people here have. I was lucky enough to see this one. They're pretty spectacular when you see them. So what you're looking at here is sunlight scattered off electrons in the atmosphere of the sun. And the structure that you see here, these lines, what you're really looking at is magnetic field lines. So what's happening here is the very hot atmosphere of the sun. It's so hot that the electrons are ripped off the atoms, so they become ions. You have electrons and ions, so they're charged particles. And charged particles gyrate around magnetic field lines. It's what they're born to do. And as a result, they travel along the magnetic field lines. And so they travel off, some of them into interplanetary space. You can see that some of these field lines are straight. They go off a long way from the sun. Some are closed, but some are straight. The straight ones let particles escape off into space. And it's those particles that accelerate away that produce this solar wind that fills all of interplanetary space and flows past the Earth as well. By the time it gets to us, it's traveling at several hundred kilometers a second. There's very little of it. There's a few particles per cubic centimeter. So to put that in context, if you had a glass of water and you expanded that out, if you had that to the same density as the solar wind near the Earth, that would be about the same volume as the moon. So it's pretty rarefied. It's much better than any vacuum we can make on Earth. It carries with it a magnetic field that's something like 10,000 times smaller than the Earth's magnetic field, which in itself is pretty weedy. But they are sufficiently important and sufficiently large that they drive the aurora and they drive other effects around the Earth. So when you look at the sun with your eye, you're not really seeing the real sun. This is really the real sun. I don't know how well this comes out. Is it possible to dim the lights a little bit? I don't know if it is or not. I'm sorry. So this is the real sun. Oh, brilliant. Thank you very much. To see this, you have to go into space. This is the sun in ultraviolet light. This is actually looking at the atmosphere of the sun here. When you look at the visible surface of the sun, the photosphere, it's at a few thousand degrees. If you go slightly higher, you get into the atmosphere of the sun. And this is hundreds of thousands of degrees. And at that point, you see a totally different phenomenon. And you see something much more active, much more dynamic. And in particular, what I hope you can see on these movies as well, I mean, they're fantastic movies, I could watch them all day, but you can see, I hope, lots of little loops everywhere. And again, they're magnetic field lines. You can't see a magnetic field line, but what you've got here is particles gyrating around magnetic field lines, trapped on those lines, bouncing backwards and forwards. Different field lines have different amounts of material at different temperatures, so they glow with different intensity. And that's why you can see variation. So there are places that look quite dark there. They're not dark, really. They've just got a slightly different population of material. And also, if you watch this thing go, you can see there are bright regions here. Underneath there would be sunspots. We call these active regions. There's a lot of heating going on. You see a lot of activity around those regions. Occasionally, things go pop like that. We'll talk about those later on as well. And again, you can see kind of some of the field lines you can see spreading out a long way further out. Oh, the sun doesn't really do that thing at the end, by the way. So these are movies from the Solar Orbiter spacecraft. We'll come back to that. So that's what the sun looks like at large scale, very complicated, very dynamic, much more dynamic than it looks to our eyes. And that's because of the interplay between the magnetic field and the particles. But that's the sun at large scale. We're looking at smaller scales as well. So let's zoom in. The smallest scale you can see here is about 100 kilometers. And you can see even on this tiny scale, it's active all the time. There's a clock going on. And what I hope you can see as well, every so often you see little flashes. There'll be a fun thing happening here in a minute. But you see little flashes going on everywhere, all that little dynamic. The magnetic fields are very strange things. We're not really used to magnetic fields. They guide the particles, but magnetic fields also carry energy. And that energy can be released through a process we call magnetic reconnection. We're not going to have time to go into that today. But that process releases energy, can accelerate particles and heat them as well. And when you see those little flashes and pops, you're releasing magnetic energy and you're accelerating particles. And with this new instrumentation, these are the highest resolution images ever made of the sun. We can resolve these processes in a way we've never been able to. Here's another one. So underneath this is a sunspot region. These are these active regions. You can see just the amount of activity that is going on here. And again, it is magnetic energy that's being released. It is accelerating particles. It's cool, isn't it? So plasmas are great. This is all plasmas, right? We're not used to plasma. We're used to neutral things like water and air. Plasmas are really strange. They do really different things. They're really extraordinary. This is what stars do, right? This is stars. Just incredible. So as I said, this material is hot enough. It's actually heated by these processes, and it flows off into interplanetary space. So this is a picture of the south pole of the sun, just because you can kind of see it more easily this way. That's the size of the Earth. And you can see this material is just kind of flowing out all the time, right? So this is the material that accelerates away to hundreds of kilometers a second, carries with it the sun's magnetic field, and forms the solar wind that blows the bubble in interstellar space. So there's a general flow, but occasionally there are one-off events that come through. So these things are called coronal mass ejections. This is an artificial eclipse made by a spacecraft, essentially. You can see stars here. There's a continuous flow, but there are these one-off ejections as well. So these are called coronal mass ejections. They carry about 1 million tons of material on average. Some of them can go rather faster than the bulk solar wind. So they generate shock waves, they accelerate particles. When they arrive at the Earth, and in particular if they have the magnetic field in the right direction, it can interact with the Earth's magnetic field, and it can generate the auroras, and it can generate some of those negative space weather effects as well. So these one-off events called coronal mass ejections are very important to us. We want to be able to predict them, and we want to know when one's going to arrive, and crucially what the magnetic field is going to be like inside. So I mentioned space weather. Let's talk about the kind of things that space weather does. So the analogy obviously is with terrestrial weather, but space weather is a bit weird. It's got some surprising effects. So let's talk from those. This is a cheesy graphic made by NOAA, which is the American equivalent of the Met Office. They're responsible for space weather forecasting as well as regular weather forecasting. It's the same in the UK. The The UK Met Office has a 24-hour space weather forecasting office down in Exeter. They make forecasts all the time. So let's talk through some of those effects. So first of all, radiation. So the sun can generate very fast-moving particles that propagate nearly at the speed of light through space. They can arrive at the Earth. They can damage spacecraft. So, we talked about that issue with the grounding of the aircraft. That's to do with very high-energy particles. They're obviously a big hazard to astronauts. The Earth's magnetic field largely shields astronauts from those effects when you're down, like in the International Space Station. We'll come back to that later on. They're also an issue these days because there's quite a lot of flights that go over the poles, particularly over the North Pole, from North America into China, for example. On those routes, because it's near where the auroral zone is, those particles can drop down and they can they generate a significant radiation dose, particularly for crew. There are crew sometimes that fly these flights that then aren't allowed to fly those flights for the rest of the year because they've got their radiation dose for the year. So you want to know when those things are going to happen, you can divert them if you need. Other effects, that radiation and actually the auroral particles arriving as well can actually heat the top of the atmosphere very slightly and it expands up very slightly. Spacecraft in low Earth orbit actually experience enhanced drag, reduced lifetimes, and they deorbit. SpaceX launched a whole set of Starlink satellites, tens of Starlink satellites in one launch a couple of years ago. They all deorbited 2 or 3 days later because the atmosphere had risen up. They didn't get a chance to boost them up before they went straight back in again. So tens of millions of dollars immediate loss. They can disrupt radio. They can also disrupt GPS signals. So precision navigation, which is surprisingly important these days in lots of strange ways. There were big solar storms in May last year, which coincided with the North American planting season. It turns out these days, farmers, tractors are all guided by GPS. And when they plant, they do precision planting and they're hands off and the tractor drives itself up and down the field so it can do the rows exactly right, plant exactly right. GPS was sufficiently disrupted and degraded for about a week that they could not plant. They had to delay planting, which had an economic loss of hundreds of millions of dollars, just for a single event, for a single impact. These things are really important. It affects the Earth's magnetic field as well, and that can actually drive currents in the ground. It can cause issues with signaling. In the UK, it's actually a big deal with the electricity grid, because it's north-south, it turns out. So the UK electricity grids really pay attention to space weather. They want to know when these kind of things are going to happen, because it really makes a difference economically as well. I've visited what's called the Space Weather Prediction Center at NOAA in Boulder a couple of times over the last year, talking to them about our data. And they actually have like the equivalent of like a war room. They have a special room. They have a daily call with the electricity grids across America to talk through what's going to happen in the next day. And they can jack themselves into the White House when one of these major events happens. So this is really serious stuff. It's taken extremely seriously. And also, incidentally, the lead guy there told me that the pigeon fanciers really pay attention to this too. So he says he gets called from the pigeon fanciers when there's a big storm coming, because they want to know. So pigeon racing is a multi-billion-dollar betting industry in North America. And individual pigeons can be worth a couple of $1 million. And they use the magnetic field to navigate. And so if there's a big storm and the Earth's magnetic field wobbles, they all get lost and they lose the pigeon. So they really want to know when this stuff happens. So that's the economic impact of space weather. So we need to know about this kind of stuff. And so we therefore need to understand the science behind it. We need to make better predictions. So enter Solar Orbiter. This is Solar Orbiter. Solar Orbiter is a European mission with American involvement. It's about a €1.5 billion mission. Thank you for your taxes. And it launched about 5 years ago. It goes closer to the sun than Mercury. It's got a heat shield on the front, a bunch of telescopes take pictures of the sun, and it's got a bunch of instruments around it to measure what's happening locally with the solar wind and the magnetic field. There's a boom at the back to get away from the spacecraft. There's an instrument on the back there with 2 sensors that measures the magnetic field, and that was built at Imperial College here. That's my instrument. So what are the kind of questions we're trying to answer with Solar Orbiter? Well, we're trying to see, you can see for the left-hand one, about the importance of the magnetic field. How is the sun's magnetic field generated? How does it affect things? What happens over the poles? You think about a bar magnet. Obviously, the poles are important for a magnet. That's true for the sun as well. How do we accelerate the solar wind? Space weather, and how do we accelerate particles? These are the kind of questions we're trying to answer. We're making good progress. I'll talk through some of that. The orbit of Solar Orbiter is really important as well. It's very clever, and it's actually quite complicated. So we launched in February 2020. So we launched just before things really got quite challenging. So one of my kind of top tips in life is never commission a space instrument during a global pandemic. It was really quite challenging. Anyway, we got going. So solar orbiter goes close to the sun. It does that with a set of flybys. We've flown past Venus multiple times, but also the Earth. Gradually, you can see it cranks the orbit in. And then we did a flyby earlier this year in February. I'll show you some data from that in a minute, where we actually went over the North Pole of Venus, which inclined the orbit slightly. And we're going to do a series of flybys now over the next few years, which is going to gradually incline the orbit up. And that lets us, for the first time ever in the inner solar system, measure what things are like out of the solar equatorial plane. And that's really important because that lets us understand the latitudinal structure of the sun and hence the global magnetic field of the sun, which drives all of this activity. So I'll show you a bit about that as well. So we did a Venus flyby earlier this year, and then we're going to do another set of them over the next few years. So this is the magnetic field instrument. I won't belabor this, it gets complicated, but Imperial College had an instrument on the UK's first ever spacecraft, Ariel 1, and we've had a essentially continuous presence in space process. So our specialization is building these tiny little instruments that measure magnetic fields. They measure magnetic fields 10,000 times smaller than the Earth's field, and they do it to a part in 1,000. They're really remarkable objects, and there's a very talented team of people that build these things. I'm not one of them, by the way. I'm a scientist. There's a bunch of engineers who do it. It's hard. It's a long business doing this stuff, so we put the proposal together, first of all, in 2008, and it finally launched in 2020. So this is a business where you have to be patient. But the instrument is working extremely well. So we launched, in February. These are not my photos. So we launched on Alex 5 from Cape Canaveral. At the time, it was the most reliable rocket in the world, so we're very happy with that. And they gave us a beautiful nighttime launch towards the moon. Absolutely spectacular. So we turned on our instrument just a few days later. We're on this boom, so we're actually turned on for the boom deploy. So that worked really well. They actually turned on our instrument less than 24 hours after launch. I was still at the post-launch party when they turned it on. It's kind of regretting the glass of wine because I thought, what if something goes wrong? But actually it didn't. It was all absolutely smooth. So it was perfect. And the instrument has performed perfectly since then. These instruments are basically computers, amongst other things. We write the software ourselves. We actually design the computer ourselves. We have a bespoke processor as well. If anyone is interested in that, I'm happy to talk about it later on, but I don't have time for it here. We deliver the data into the archive. We've actually developed a new compression algorithm along the way. For anyone who's interested in such things, I will say a fact. Any positive integer can be expressed as the sum of non-consecutive Fibonacci numbers. That turns out to be true, and with that you can compress data, it turns out. So it's just amazing. We've got very clever software people too. We've delivered many billions of magnetic field vectors, and this instrument so far has cost about £5 million. And this is just an example of the kind of data. This is the magnetic field that we measure. It's a vector, 3 components of the magnitude. This thing here goes rock like this, so the magnitude goes up by a factor of 20 or 30%. You see all the wiggles. That's a collisionless shock wave in space. So that's a shock wave caused by one of these coronal mass ejections. Those wiggles that you see are the magnetic field being moved around by protons gyrating around the magnetic field. We can do really complicated microphysics. We've flown past Venus. This is the magnetic field over Venus. Venus doesn't have a global magnetic field like the Earth, but it's got a dense enough atmosphere that if you go close enough, you get to a region where the magnetic field is excluded by the top of the atmosphere. We went over the North Pole. We skimmed over the top of the cloud tops, just at a few hundred kilometers. So closer to the Venus than the International Space Station is to Earth, right over the top. So you can see these little magnetic field vectors, and you can see that they're actually excluded as we go over the top by the atmosphere of Venus. And we can measure this global magnetic field now. So I said we're going out of the equatorial plane. We can do this for the first time now. So what I'm going to show you, this is really early results. This isn't published yet. And this is my kind of attempt to try and portray what it is we're doing here. What you're going to see here, the central sphere here is the sun. And this is like a simulated view of what the spacecraft sees. As we rocked up and down in latitude, you'll see us go close to the sun, we'll rock down and then up. We measure the magnetic field of the spacecraft. We can work out where that comes from on the sun. We can therefore start making global maps of the magnetic field of the sun. So that's what this is. So the color here, blue and red, tells you whether it's outward or inward polarity magnetic field. And as the sun rotates underneath us, we can gradually build up this map. So if you think about a bar magnet, you would expect half of it to be red and half of it to be blue, right? You should sit one half north, one half south. And if you look as the spacecraft gradually builds up the map, that's absolutely not what you're seeing. You're seeing red patches and blue patches. You're seeing this global magnetic field. And it is absolutely not one in the north and one in the south. And if you actually try and think about this as a magnet, it's a magnet pointing almost exactly horizontal. Right? This is the global magnetic field of the sun. Near this solar maximum, it's actually such a complicated field that the global field is not north-south at all, it's sideways. This is our first map like this. We do this every 5 months now, and we're going to be doing this over the next few years, and for the first time ever, understand the global evolution of the magnetic field of a star as it goes through a solar cycle. We've never been able to do this before. This is brand new. But it's early days. We've just started getting this data now. So I also want to talk a little bit about Parker Solar Probe. This is the one on the right here. Solar Orbiter goes closer than Mercury. It is the second closest spacecraft ever to the sun. So it gets about 60 solar radii away from the sun. Parker Solar Probe on the right is the closest, and it launched in 2018, and it gets 10 solar radii, incredibly close. So if you think about the distance of us from the sun as being a meter, let's say, Mercury is about 30 centimeters away from the sun, so Solar Orbiter gets to that kind of distance. Parker Solar Probe gets to 5 centimeters away from the sun, and that's close enough to actually be flying through the atmosphere of the star. And it's taking really revolutionary measurements. It's doing some amazing things. I won't go into all the nitty-gritty detail, but I wanted to play you one movie. And before I do, what I should just say, so this is an artificial eclipse movie taken by Parker Solar Probe. You can't look at the sun this close. The instruments would melt, so it's looking out to the right-hand side. It's going to fly past the sun. You see the sun is on the left-hand side here. It's that little dot there, and it will get closer as we get closer to the sun. That's there, the distance in solar radii, 53. We'll go down to about 10. And what you'll see is solar wind flowing away. So these are very deep cameras. You see all the stars. These are very, very deep cameras. It's like making an artificial eclipse. You'll see flow coming outwards. But as we get closer, you think about that eclipse picture that we saw nearer the beginning from the May 24 eclipse. You see all that kind of striation structure, all those little fingers. You're going to see that, but you're actually going to see the spacecraft fly through it. So you're going to see it like flying through that eclipse picture. You'll see coronal mass ejections going out as well. But what I would say is what we discovered on flying Parker Solar Probe is that close to the sun, there's a lot of dust. The spacecraft is flying tens of kilometers a second, over 100 kilometers a second. Those dust particles hit it. They sputter off lots of little particles, and they end up as streaks in these movies. And so it does flash quite a lot. So if you're at all susceptible to anything kind of flashing, I would not watch this movie. I would close your eye. It'll just last a minute. So you see the flow coming out from the sun all the time on the left-hand side. There are one-off events like coronal mass ejections. You see all the flickers. This is from the dust. The cadence of the images changes, which is why it seems like the sun's slowed down, but it hasn't really. And so as we're gradually getting close to the sun, that's about 25 solar radii. You see these rays gradually start getting brighter. You see individual things going past. And then as we start getting closer, can you see we're actually kind of running into the rays and actually flying through them. And then look at the flow coming through the coronal mass ejection. That's what it looks like to be inside the atmosphere of a star. So these are extraordinary movies, I think. And again, these are really new. We're just barely beginning to understand these things. And there's a comet. There's always a comet. Solar Orbiter flew through the tail of a comet. I mean, by accident, right? We didn't even plan to do it. So they're everywhere. Okay. So we have Parker and we have Solar Orbiter. There are other spacecraft flying around as well. This is just a view of the solar system. So you are the blue dot. The sun is the yellow dot. And all of these things are spacecraft. This is Solar Orbiter. So over the last few years, we've got this renaissance of studying the sun because we've got all these spacecraft flying around together. There's one which is on its way to Mercury, back to Colombo. There's a slight, this one here, I should say, is a very boring one. This is stereo, it doesn't really go anywhere. But one thing you can see is there are times when they get close together, different spacecraft. There are also times when two of them line up along the same direction away from the sun. And they're incredibly important because we can see how the solar wind evolves from one distance to another. But there are also times, if you look at Solar Orbiter, the red one, there are times when Solar Orbiter goes upstream of the Earth. And we get real-time data from Solar Orbiter. Now, at this moment in time, Solar Orbiter is being tracked by a dish, and we're getting real measurements from my instrument right here, right now. And that lets us look at what's going to happen and arrive at the Earth sometime later, like there are times later. So there's lots of things we can do with these multiple spacecraft together, and that really is producing really rich science. I'm not going to go into this in great detail, but one of the key things that we want to understand is how does the sun make this solar wind? How does it travel so fast? The solar wind can travel up to 800 kilometers a second. And actually, rather remarkably, You imagine like, so things are leaving the sun, particles are leaving the sun, like things leaving the earth. So imagine if you have like a tennis ball or something, you throw it up in the air, it slows down. So the solar wind, these particles leaving the sun, you expect them to slow down. They don't, they accelerate. So if you look at this plot here, this is a plot distance away from the sun, and this is the speed of the plasma. We can measure it at Parker, and then we can measure it at solar orbit. It's faster. It's actually accelerated as it goes away from the sun. And we can now measure all the different energies, the different contributions to the kinetic energy and so on, of the plasma at multiple places on the same streamline, and understand how this is happening for the first time. And actually, I showed you those movies of the sun right at the beginning. You remember me saying about all those little pops? You see all those little bright points going off, releasing magnetic energy? That magnetic energy, there's little impulses, they're little pulses that go out into the solar wind. And we now know it's those little pulses that add up the extra energy that makes the solar wind the speed that it is. So we can understand for the first time how stars make these winds and how they get to the speeds that they have. We've never been able to do this. So I mentioned space weather, and so, as I said, there are times when solar orbiter is upstream of the Earth. And that's a time when we get this real-time data, we can actually tell people what's going to arrive at the Earth far farther ahead than has ever been possible before. This is an example from a European Space Agency press release. So at this point, we were something like half of the distance from the sun to the Earth, upstream of the Earth. This is our magnetic field measurements. The details don't matter, but this magnetic field, this is what arrived at the Earth a couple of days later. You can see it's basically the same. And crucially, we could tell from this event it was a very big event, it was a fast event, but also the magnetic field was going to be in exactly the right orientation to trigger a very big storm. This is the days when we were tweeting, and we had thousands of followers, so the solar orbiter magnetometer would tweet. And what I used to tweet was just little time series plots of magnetic field vectors, which are spectacularly boring, and you don't expect anyone to be interested. We would have 60,000 people looking at those plots. And that's because the aurora hunters care. And they know perfectly well how important this stuff is. So these are images taken in Canada and North America of the auroras that were generated by this event, because we told them it was going to happen, and the people went out in the middle of the night and they took the photo. This actually produced a very big storm. So we are now working hard with the space weather prediction officers in the UK and America and other places around Europe. We provide them data in real time so they can use it to improve their forecast. It doesn't always work because we're not always lined up. At the moment, we're actually quite well lined up. We have a website where these plots are publicly available. You can look at these. This is the data from now. While I was standing at the back just now while Mrs. President was talking, I actually just uploaded this, so this plot was made less than an hour ago. So this is the position of solar orbiter now. There's the sun, there's the Earth. So solar orbiter is just off to the right-hand side, and this is magnetic field structure that will probably arrive at the Earth in a day or so. Okay, I want to talk very briefly, if I may, about another mission as well. So solar orbiter is doing a great job in the inner solar system. But the latest NASA mission in understanding heliophysics, understanding the sun, is a mission called IMAP, the Interstellar Mapping and Acceleration Probe. Entirely NASA mission with 10 instruments on board. 2 of them are contributed from outside the US, one from Poland and one from the UK. And that's the magnetic field instrument from Imperial College. And again, you see there's a boom, and our instruments sit on the boom. So this is IMAP. It's quite an ugly spacecraft, I have to say. It's quite boring, but nevertheless, it is what it is. It does a great job. It's just not much to look at. So it rotates, as you could see in the previous movie. That's the boom with our sensors on it there. The boom deploys after launch. This is it on the rocket, stowed. It actually flew with another couple of spacecraft as well on here. I'll talk to you about that later. So this is it just before it gets encapsulated onto the fairing. And IMAP does a very different job to solar orbiter. So IMAP, with those 2 other spacecraft called SWIFO and Carruthers, I'll talk about one of those later on, launched from the Earth in September. If you look at the dates on the left-hand side, they're live now, so you can see this is kind of about now. And it's going something called the first Lagrangian point, L1. If you know about James Webb Space Telescope, that's gone to the second Lagrangian point, L2, which is behind the Earth. This one is upstream. So you can see on the left-hand side, there's the Earth, there's the moon going around, and that sort of bubble structure, you can see that's the Earth's magnetic field. That's our protected magnetic field. So these spacecraft go upstream, and SWIFO and IMAP are measuring the magnetic field and the plasma conditions upstream so that we can give warning about what's going to happen. This is not very far upstream. you see, relative to the moon. So actually, this only gives us about half an hour, 45 minutes notice. But they're there all the time, and so we can make those measurements all the time. There has been a spacecraft there doing that job. There's one there now doing it. It's more than 25 years old. It's called the Advanced Composition Explorer. It's running out of fuel. And so it became really urgent to get these spacecraft out there to make these measurements. So these measurements are used routinely by space weather forecasters all day, every day. So it was really important to get this done. As you see, the spacecraft has launched. And so everything's going really well. I'll just play you the launch video.
6, 5, 4, 3, 2, 1. Engines full power. And liftoff. Go Falcon. Go IMAP. Go Swiftle. Go Brothers.
And we are flying 3 new missions on a million-mile journey to track space weather. Good looking flight so far. Our tracking cameras getting a great shot.
That's right. So coming up is max Q, which is the maximum aerodynamic pressure, largest structural load the vehicle will experience. So slowing it down helps to reduce some of the load it
Falcon 9 is
experiences.
supersonic.
And that will help us recover and reuse the first stage.
Max Q.
Just 30 more seconds on that stage 2 burn. And then we'll cut it off and coast for quite a while.
Quite a while until we get to the right point in space to fire it again to put us in our final destination.
Stage 1 transonic. And back shutdown.
We're going to impact shutdown. So you can see it there in the image right there.
There we go. That's that 4 revolutions per minute we were talking about. That is not something that is wrong. That is intentional. We're looking forward any moment now when we can have separation of the IMAP spacecraft.
Pretty cool.
IMAP deploy confirmed.
There we go. IMAP has separated, beginning its mission to map to the solar frontier and reveal how the sun shapes our space environment.
No IMAP.
So IMAP launched on a Falcon 9, which is currently the world's most reliable rocket. So we are very happy with that. It launched from Cape Canaveral. It launched from Launch Complex 39A. So, which I didn't really understand the significance of before, but I do now. So Launch Complex 39A is the Apollo program. So anyone who's walked on the moon has launched from a single spot on it. So that's where we launched from. It was really, really cool. It was a beautiful dawn launch, really, really spectacular. So as you see, the spacecraft deployed from the upper stage at the end, and actually the upper stage had to spin to deploy IMAP because it spins. So SpaceX had never deployed a spinning spacecraft before. So we were really quite nervous about it, but it all worked really well. I was there for the launch, watched the launch. The deployment, so getting into space takes 10 or 15 minutes. It then coasts for about an hour and a half, and then it did the deployment off the end. IMAP actually deployed off the top of the second stage while I was stuck in a traffic jam outside Orlando Airport because we watched the launch, said good, and ran and got in a car and drove because we had to get into Colorado because the boom was deploying not long afterwards, and we had to be there to commission the instrument and make sure everything was okay. So it was an extraordinarily intense couple of weeks. Launch campaigns are nothing like anything else. They're really extraordinary things. But anyway, it's all worked extremely well. So the data's all embargoed at the moment, so I can't really talk about it very much. But I'll just show you a plot anyway. But everything is actually working extremely well, right? So the instrument is working outstandingly well. The whole spacecraft is working well. As we speak now, actually, the spacecraft is in a path. It's communicating with one of the antennas in Goldstone on the Deep Space Network at the moment. So just before we came in from coffee, we actually, a couple of my engineers were on the line. We actually did a small update into the instrument, a final configuration update into the instrument. So we're in our full operational configuration. So that just happened this afternoon. So the sun rose over California, the dish point of the spacecraft. And they did it very quickly just now, so it was very smooth. I was a bit nervous. I was worried I was going to have to run and not be able to give this talk, but actually everything went fine, so we're all happy. So this is actually a measure of the magnetic field from, you see, started from November the 11th. This was a very large coronal mass ejection that went past the Earth. This caused a very large storm. It actually caused auroras over the UK, but it was cloudy, so nobody got to see it. But this is actually a very large event, and it was one of the largest events at the Earth in terms of energetic particles for a couple of decades. Really very strong event. What's called a ground level event. And actually, it was there were sufficient numbers of energetic particles. They actually caused significant upsets to quite a few instruments on quite a few spacecraft around the solar system. So I'm not in a position to say what they were, but quite a few were affected by this event. Our instrument actually is a real trooper. So this is a very similar to the one on Solar Orbiter. So we measure this thing that happened to the Airbus planes are what's called single event upsets, where it basically corrupts a little bit of memory. So a particle whizzes through it and just sort of flips a single bit of memory. Our instruments are robust to that, but they do count. And we get roughly, on average, one of those a day, about one and a half a day on average. During this event, we got about 20. Solar Orbiter went through a very big storm on the other side of the sun in August, and we had over 170 in a day. So sometimes these are really, really extreme events, but the instruments are designed to be robust, and they work. Okay, so I'm going to wrap up in a minute. There's one thing I just wanted to talk about in terms of space weather, and that's astronauts. So I mentioned that the radiation is a hazard to astronauts, but actually they're largely shielded by the Earth's magnetic field. So the astronauts on the space station are susceptible to these effects, but the Earth's magnetic field shields us from a lot of that radiation. No human has been outside the Earth's magnetic field for more than 50 years. But in the next year, that's going to change. So the Artemis program is NASA's program to return people to the moon. Artemis 1, the first mission, has already flown. It didn't have any people on it. So a spacecraft went round the moon and came back again. That takes about 10 days. Artemis 2 is due to launch, if everything stays on schedule, in early February. It might slip, but at the moment, that's the schedule. It will carry these 4 astronauts. They will not land on the moon either, but they will go around the moon and back. And it's the first time that we've had people outside the protective environment of the Earth's magnetic field since we've understood what space weather is and since we've had assets in place to be able to predict it. So NASA is understandably extremely focused on making sure that they can predict these events and do the best we can for the astronauts. So the instruments that we build at Imperial College, Solar Orbiter will be upstream at that point, so we'll be able to provide far upstream warning from Solar Orbiter. And also IMAP will be NASA's space weather mission upstream of the moon to make those predictions. So we'll be playing our role, a small role, but we'll be playing our role in that as well. So that's something that we're really gearing up to and working with the teams in the US to try and make sure that everything is robust and in place so that we can support that mission as best we can. Okay, and I want to just finish. I mean, I've talked about science here and I guess space weather as well, but I haven't really talked about the people that build these instruments. I think it's really easy to give a talk about the science. You know, the pictures are lovely and everything else is fine. But there are people here who build these things. And this is the team of people that build the IMAP magnetometer at Imperial College. They're a remarkable team of people. They're not exceptional people, they're just very good people. And they're doing exceptional work. And they're an amazing bunch. There's people who run marathons, there's people who used to work at the BBC, there's someone who used to work at the company that makes ejection seats for fighter jets. There's someone who started their own football team. There's someone who's played on the main stage in Glastonbury. You know, they're a really quite remarkable set of people from that point of view. But they're people, but they work hard. And they do, I think, amazing things. So I was taught by a good friend of mine many years ago that every photo is better with double thumbs up in it. And so IMAP Mag became a double thumbs up mission. So this is all of us. And actually, the photo in the middle is us underneath the Saturn V boosted about half an hour before IMAP launched. So they're a great bunch. But I think I would just say it's important whenever you see any science, a space story, but anything, and you know this perfectly well from large telescopes as well, there's a bunch of engineers who are making those things work. And they're incredibly important people. And I don't think we talk about them enough. I don't think we celebrate them enough. And so it was great to see some of your awards today. It was very much about making instruments and operating instruments. I think obviously this is a bunch of people who understand that very well. But I think overall in the world, that's a story that we don't tell enough. And I think we should try and do more because they're the people that make all of this. Okay, with that I will end. Thank you very much. So it's a really exciting time in space physics at the moment in understanding the sun. We've got a really fantastic bunch of spacecraft. Almost by chance, they've ended up in launching at about the same kind of time. It was not the original plan, but as a result, we've got a fleet. And that fleet is helping us understand the sun and hence stars in ways that we've never seen possible before. And it's helping us improve our predictions of space weather and helping keep everybody safe at the same time. Thanks very much.
That was quite a run through what's going on up there. Scary, really. I don't think an umbrella is going to be much use against that kind of weather. So let's open up the floor to questions, please, ladies and gentlemen. Gentlemen here, we have microphones so that those watching on YouTube can hear the question.
I just wondered if you knew what the mass contained in that huge coronal mass ejection was, what you talked about.
Yeah, so the ballpark is 1 million tons.
Yeah, but this was bigger than...
Yeah, so they can, I mean, some of them are really tiddly, so some of them are like 100 times smaller than that. They don't get a lot more than that. The absolute figure for that one I do not know, I must admit, but they're that kind of order, yeah.
Oh, okay.
But what makes them particularly effective is a combination of how fast they're going, how dense the material is inside them, and which way the magnetic field points. And it's that congruous of all three. So you can have a really dense event. If the magnetic field points the wrong way, nothing very much happens. And sometimes you can have ones that actually really, they can be fast, not a lot of material in them, but just fast, and if the magnetic field points the right way, it goes. So it's a really kind of subtle combination of all of those.
And the material's just isolated protons, is it, mainly?
Yeah, so the sun is made mostly of protons, and so they come out with electrons because they have to be charged neutral. So the electrons come along for the ride.
Oh, they do. Okay.
And there's little bits of other things. There's a few percent of doubly ionized helium, so alpha particles, and then little bits of other things too: carbon, oxygen, neon, a few other bits and pieces. We're all born of the same nebula originally, so all that stuff comes out too. And actually, what those other heavy ions do is really interesting as well. And actually, although I didn't really have time to talk about it very much, we measure these magnetic fields extraordinarily precisely. Those particles are measured extraordinarily precisely too. There are instruments that can measure the particles coming from the sun and even neutral atoms floating around the solar system. And they can not only tell you how fast they were going, individual atoms, how fast they're going, what direction they came from. They can even say, that one's carbon, that one's nitrogen, that one's atom by atom. It's absolutely...
Jerry.
Hi, it's a marvellous presentation, so clear and brilliant visuals, I have to say, as well. I should mention that I've actually stood in the flame trench at pad 39.
That's good.
But when not during a launch.
No, at a rather quieter time. You mentioned how the particles from the sun actually go out and are accelerating, which is somewhat similar to the acceleration of the universe in general, which we believe due to dark matter. So what has been proposed as the reason for this happening with the solar particles?
So the original acceleration, if you think about the Earth, so we have gravity and an atmosphere. And the atmosphere, obviously, it gets less dense higher up, but there's still some higher up. But essentially, it's gravitationally bound in the sense that the density of material drops off faster than the Earth's gravity drops off, so it never actually gets to escape. So one of the key things that was realized by a guy called Gene Parker in the 60s is that the sun's atmosphere is so hot that scale height, the height at which the atmosphere drops off in density, is actually quite large compared to the radius of the sun. And so it starts expanding away as the gravity kind of drops, and it manages to get out, get away. That wouldn't necessarily go on forever if there was a larger density in interstellar medium. And so he realized that actually it's the density gradient, the pressure gradient between the sun's atmosphere and interstellar space that helps it keep accelerating. So we knew that it was accelerating. It's actually, mathematically, it's the opposite of a Laval nozzle. So it's like the opposite of a rocket engine, kind of going the other way. So we realized that we knew that the solar wind was going to accelerate. That had been realized since the 60s. But those models can't make it fast enough. So there had to be an extra source of energy to get to the speeds that we have. And that's the critical realization of the last few years, that there are these impulsive events. So each one of which so we fly along, and you measure the solar wind, and it's doing a few hundred kilometers a second, maybe 300 or 400 kilometers a second. Suddenly you can have, for 20 or 30 seconds, wind that is going 200 kilometers a second faster than that, and then back down again. So it's got more than twice the kinetic energy, and then back down again. And those are little those are little bursts of particles which are generated, we think, from these magnetic reconnection events down on the sun. So we're managing to tie all these things together. It's that extra energy that gradually pulls up the wind that it's got.
Thomas, you have a question?
Very interesting talk. Thank you very much. And I was just wondering, to do with the shielding on the electronics, is that a sort of the way the circuit is manufactured, or is it layers of metal on top that shield the
Yes,
processing?
it's the way they're made. So these are special radiation tolerant parts. So they're very expensive. I mean, really expensive. We buy chips that cost £20,000. And so the memory, for example, if you say I'm going to have, I don't know, like 32-bit memory, it isn't 32 bits. It's got a whole bunch of extra bits, which are all checksums. And so when the computer, it reads a bit of memory, it checks against the checksum. And if the checksum's wrong, it knows it's been corrupted. But it has enough extra information there to be able to correct it. I mean, don't ask me how. So a single upset we can correct. So when it reads it, it realizes it's wrong, fixes it, and puts it back.
Nice.
And actually, we have what's called scrubbing. So all day, every day, it's going through the memory and it's fixing it for single errors. Double errors, you have no idea, and the computer panics. But single errors, we've never had a double error, and I'm told that statistically you need about 1 million years to get a double error. So I think we're okay. But single errors we fix all day, every day. It's actually, if you're interested, I'm happy to talk about it afterwards. I find it's very nerdy, but it's actually really interesting.
I work in electronics. It's really interesting.
Yeah, let's have a chat. It's fascinating. Yeah.
Thanks.
Did you have a question, sir, in front here?
Yeah. Hi, wonderful presentation. Can I just ask about the physicality of these magnetometers that you're building? The size of them,
Yeah,
the
okay.
weight of them, and I think I probably know the answer to this anyway. But why all your stuff gets stuck on the end of an arm, very far away from the rest of the ship?
All very good questions. So the sensors you can hold in your hand, they're about that big. They weigh a few hundred grams. The electronics box is about that big, weighs 2 or 3 kilograms. And then we've got all this complicated harnessing and wiring that kind of puts them all together. They consume a few watts, 7 or 8 watts, including heaters. So Solar Orbiter, if you look at the picture of the spacecraft, the boom's at the back. It's actually in shadow. So our sensors, we have heaters on them to keep them warm. So the front of the spacecraft's at about 300 or 400 degrees. Our sensors are heated to keep them at minus 90 degrees. And the spacecraft, to my intense irritation earlier this year, actually, in March, the spacecraft had a problem and they turned the heaters off and we got down to minus 134 degrees. We were not at all sure it was still going to work. They're away on a boom because every time you put a current in a wire, you make a magnetic field. And the magnetic fields we want to measure are so extraordinarily small that we need to, the spacecraft team work incredibly hard to minimize the magnetic fields that the spacecraft will make. But even so, there's nothing better than just getting away from it. So we work really hard to try and get those instruments as far away from the spacecraft as possible. It's always a trade. We really wanted the boom to be longer. We always want the boom to be longer. This is about 3 meters. Actually, if I show you the top right photo here, is when we did a final magnetic test on the spacecraft. So that's in the clean room of a place called Astrotech. It's near the Cape, so it was just before launch, before it was encapsulated. We did a final magnetic check of the spacecraft. So that's us in the one on the right who's looking very excited is me. So we go through an enormous amount of effort to try and reduce magnetic fields from the spacecraft. But that's why we put them on booms to get away.
Can I just check were there any questions on YouTube from our YouTube people? No? No, okay. Any more questions?
There's one down here.
Sir?
Yeah, what's the count of the 19th century? Is it possible to say on the subject of shielding whether that was very exceptional, or is just our shielding that much better today that we don't need to worry?
Right, yeah, so for those online, that was a question about the Carrington event, which is a famous event in 1859, I think. The idea is if one of those happened now, it would be a major disruption. So, as we say, we designed a lot of this stuff to be as robust as possible. But even so, anomalies do occur, and they did recently in the last month as well. So it's really hard to know, and it's really hard to know exactly what the Carrington event was actually like in terms of, for example, the energetic particle environment at that time. It's incredibly difficult to know. We've had events other places in the solar, so these things, when these coronal mass ejections, sometimes they go past the Earth, but they don't have to. They can go in lots of directions. And we've had cases with spacecraft in other places that have gone through very, very intense events. And actually the one that Orbiter went through last August is an extraordinarily intense event. So it's really hard to know, but equally, sometimes the effects come from other things which are not just those kind of things. As I said, that you can degrade GPS, those kind of things. So we are now dependent in so many subtle and interconnected ways that it's very hard to know quite what a Carrington event would do. For example, one of the big worries is the electricity grid. So, Spain earlier this year lost its electricity grid, right? It went down, nothing to do with space weather, but it went down. The whole of the Iberian Peninsula went down. And it took them most of the day to get it back up again. Rebooting a grid from scratch is incredibly difficult because nobody ever does it. And actually, they were getting very tense by the end of the day. So if you're running a hospital, you have a backup generator, how much fuel have you got in your backup generator? How long is it going to last? So what's the requirement for how much fuel you have for all of these kind of really critical services, how long do they run? And if you actually, all of those things start running out, if you don't get your grid back up in a day or two, everything starts falling apart. So actually, I should say the UK government has what's called the UK National Risk Register. It maintains a risk register. Space weather is very high up that risk register. So the government understands that this is something that's really significant. If you blow a few substations, there are a very small number of substations in the electricity grid across the UK, which is like the size of a house. The UK holds, one as a backup, and they take 6 months to build. If you blow 3 or 4 of them, what would you like to do next? So the system is people are trying to mitigate things. They design in as much mitigation as they can, but it's that the risk is hard to quantify and hard to understand because we haven't had one of those kind of events in the modern era. And so that's the concern, is to try and understand how bad could they be and what would you do if one was going to happen. So if someone tells you now, right, 6 hours time, one of those is going to hit the Earth, what would you like to do next? And I think that's the challenge, is trying to understand what society should do to prepare and how much resource is worth putting into that on the basis that it might never happen. But if it does happen and things are bad, we really would be grateful for having put that work. It's a very difficult trade, and I understand governments find this extraordinarily difficult to deal with because it's very hard you can't say it's going to happen. It's almost like the Icelandic eruption that knocked out air travel for a week or so. If someone had said, oh, well, there's a risk of knocking out air travel, we're not going to do anything, it's going to be fine. And then it happens, and then you say, okay, I know that is a big problem. And so the risk is that we have a big space weather event, and only then do we realize that we should do something. And we would regret not having done more.
You remind me, in a previous life, I was part of the contingency planning for the Olympics, and how we were going to police London, for want of a better phrase, during that time. And I remember, this is around 2010, 2011, trying to say, there is this thing called the Carrington event, and if it hits, we will lose all our radio communications and whatnot. And the difficulty is trying to get people to hear that message. And I basically was treated as if I was off another planet. Some might say yes, but, it was just
it's like,
don't be ridiculous. And that is a real problem.
I think that's right. Yeah. So people will say, well, what would you like me to do?
Yes.
Right? Yeah. And I think this is the problem. So this is the argument for doing the research to try and understand this better. And as I say, to try and make better predictions. So one of the things we really want is to be able to have better further upstream warning.
Yeah.
Because actually, as I say, these things at L1, they give you maybe 45 minutes notice. That's not a lot. But the argument always is, give me like 3 hours, give me 4 hours. Because, for example, one of the things people could do is they can stop doing maintenance on the system. Because if you're in the middle of doing a big maintenance activity and something happens, then actually you're much more risk.
Yeah.
So, and the other thing that someone always said to me is, like, in the middle of the night, the people that you've got running the electricity grid, they're great, but they're very much a skeleton crew in the middle of the night.
Yeah.
And how long so it turns out 3 hours is enough time to pick up the phone, to call your A team, to get them out of bed, to get a coffee in them, and to get them into the control room. Because sometimes that's what you want.
Well, I was unlucky enough to be in Spain when they had the big power cut, and it was tragic because all the beer started getting warm. I didn't know what to do. You know?
Well, you will be unsurprised to learn that the European Space Agency had backup power for all of its communication dishes, and everything just kept going.
Fantastic.
Because they understand space well.
Well, I think we've taxed you enough with our questions, but I know you're going to stay around for a cup of coffee and maybe later afterwards. So may I please ask you to thank Professor Horbury again and his lecture.